Of course, we would need to properly define what we mean by symbolic versus sub-symbolic. Typically, I take a rather pragmatic stance with symbolic being a localist representation, that is one that can be manipulated by setting a pointer in some way, and a sub-symbolic one that is distributed, that requires us to look at an assembly or a population of representational elements to understand what they are representing. And it seems for human cognition that we clearly need both, because there is a lot of perceptual content and memory content and so on, and also operations working on those that require associations and vagueness and the co-activation of many attributes in varying degrees to express a certain concept properly, because the concepts themselves that we need to encode are often vague. Domains that we need to specify are might have fuzzy boundaries and so on. On the other hand, we cannot make do without symbolic representations in the sense that I just mentioned, because if you want to use learn language, or if you want to learn things, you need to have pointers that can organize concepts in different ways. So it's important that you are in some sense able to take your representations, cut them apart, and reconnect them in other ways. And this is what I would call symbolic processing. And I think in this sense you need both, and you need to find ways to reconcile them in your architecture.
Yeah, I totally agree. In fact, our system tries to combine the sub-symbolic capabilities of a tag with symbolic representation of standard ontologies in general, and we are trying to integrate those two different representational systems, let's say, and because we think that, per se, the task of building knowledge systems or artificial general intelligence systems is possible only if you try to integrate both these two different approaches. So my answer to you is they are both important for us, and that's why we're trying to expand the knowledge part of ATAR in order to get more symbolic knowledge into a sub-symbolic, basically sub-symbolic architecture.
Yeah, I think we both are important, and another one, in addition to what Joscha said, symbolic representation is also important for reasoning, which we cannot easily do without.
Yeah, no surprise I'm going to say both are good, but my approach is different. I don't use an integration of a symbolic part or sub-symbolic part into a system like actor and some other system. What I have is, in my system, actually there are two interpretations of the same architecture. I typically represent that as a reasoning system, as a logic, so many people say, oh, it's pure symbolic. But on the other hand, I can equally interpret it as a network, because all those concepts, for example, have a distributed representation in the sense that the meaning of a term is fully determined by its relationship with all the other terms. So it doesn't use traditional, say, model theoretic interpretation at all. And also the reasoning process, in a sense you can see it, it's very similar to activation spreading. So to me, it's just two different perspectives of the same architecture.
Yeah, I'd like to say that from a perspective of CREST, it might be a question of scale. So on one level, when we're looking at CREST and simple patterns, it looks very symbolic. If I look at the interpretation that CREST gives of a chess position, and what it does when it looks at the chess position, it might look at 20 or 30 chunks and touch on the various bits of the knowledge inside it. And this is a fairly distributed sort of representation, and takes on some of the characteristics of what are attributed to sub-symbolic representations. So I think there's some of the properties that can be held up with this sort of symbolic representation, depending on what scale you look at.
Maybe as a small extension, I think that most of us to varying degrees support the idea that there should be a single representation mechanism for symbolic and sub-symbolic operations. But this should not cloud our vision. This is just our working hypothesis. And there could be other people in this panel, for instance, Ron Sun with his architecture Clarion, and he has two different sets of operations that work on either symbolic sets of representational elements and or sub-symbolic representations, and then there are some conversion and translation mechanisms. And some of the processes which go on in the brain can be interpreted as being translations, or it seems that there are different sets of operators working maybe on the same representational units, like a prefrontal cortex extending pointer into the rest of the cortex and manipulating representations which otherwise would only work associatively. But as I said, this is an open question. It's an open research problem in my view.
Aaron Sloman, Birmingham University. I've got a worry about what we've heard and what I suspect we're going to hear in the rest of this conference. And people who've been around since the 70s, 80s, and 90s may all share this worry. We've heard a lot of presentations of particular designs, and I suspect there are people around the world who could have given another 20 or 30 presentations of architectures for cognition or something. And that worries me because I don't see anybody I don't see the community, to be more precise, referring to a common collection of concepts that are relevant to architectures, a common collection of design options that are available for architecture, a common collection of criteria for selecting what has to go into architecture, a common collection of ways of evaluating what you've done and deciding whether you got it wrong. And in particular, I don't see anybody talking about architectures that don't start fully formed, but grow themselves, which is certainly true of humans. A newborn baby doesn't have most of what a one-year-old has. Well, it might have most, but it doesn't have anything like all the components. And a 4-year-old is different again, and a professor of quantum physics is different again. So I feel there's a lot of scrabbling around in various dark corners of the space of possible designs, and I don't see a science at work here. Now, have I missed something?
Anybody want to start?
Yeah. First, I will say I fully understand the concern. Actually, I worry about the same thing myself, and many people actually take that as the major problem in the AGI community. The first thing I want to mention is this thing have been noticed by many people, and actually many people have been trying to do these things. We have seen many proposals and papers in previous conference on some common framework, common terminology, evaluation approach. But the reality, you're absolutely right. None of them have been accepted by most of the people. To me, my interpretation is this. I don't think it's because the people here don't want to cooperate, or well, I cannot say there's no such an issue, but I don't think that's the major issue. Actually, everyone I know in the community want to cooperate. It's just we simply don't have the same idea. I cannot convince you, you cannot convince me. So at the moment, maybe the best thing is we develop our idea in parallel, but in the same time, using opportunity like this one to communicate. Let's see how much we can agree, how much we can cooperate. I want to cooperate, but I don't want to cooperate just because cooperate is good. I have to cooperate with someone with whose idea I basically agree. We can live with minor difference. So to me, it's just a matter of complexity of the field and the difficulty of the problem.
Well, perhaps one thing that could be done is for everybody to say what they didn't do and why they didn't do it.
Yes, fully agree.
Sure. Anyone else on the panel? I'd just like to say that maybe some of this is natural because people really, there is no standard definition for intelligence. So to start with, people are working on different definition.
He's not mistaken.
Oh, okay. So, it's okay. There is no standard definition for intelligence that everyone agrees upon, for starters. And the second thing is that the end goal for different researchers isn't always the same. Some people want to build practical systems, other people want to validate psychological models. So I think some of this is natural.
There's a G in generality.
And this is also true for ontologies. I come from that kind of research area, and the discussion about shared ontology or trying to build top ontologies, top ontology, and agree on that, agree on the choices, has been around for years, and no one agreed on that. So what we can do right now is mapping ontologies, mapping models, having good methodologies and good instruments to map the models. And probably this can be done also at the level of architectures. Try to make architectures communicate. Of course, in order to do that, you have to, in advance, you have to have like a list of things, a meta model of all these architectures, of all these ontologies. This is my.
I think at the moment we are learning a lot from each other. I've learned a lot from reading John Anderson's books about ACT-R. I'm learning things from Pei, I'm learning things from Ben and from many others, and I also get invited by people, and then I find bits and pieces of what I did in their work, which I think is a very good thing. I don't think that a big collaborative effort can be organized simply top-down by prescribing a certain architecture like ACT-R, which would be fixing a paradigm in ways that are maybe not productive, because this is just a particular perspective which is good at a certain stage of understanding. And if you look at the world at large, for instance, how do programming languages evolve, what we need to achieve are critical masses, lots of people working on these problems, a much bigger community than this one, before we can think about spreading paradigms much better than we do now. At the moment we are a very small community, I think, and we shouldn't forget that given that we are such a small community, I don't think we are doing too badly, even though it's limited.
Paul?
So I'm Paul Rosenblum. Instead of asking one general question for the whole panel, I'd throw three short ones at individuals. On CREST, the question is, so discrimination networks are one representation of knowledge, and they're one that's been used traditionally for learning and can provide generalization and partial match. But it's by far not the only such representation, the only such learning algorithm. The question for you is there something specific about discrimination networks and EPAM-like learning that is important for the kinds of results you're trying to generate? Or would any kind of generalization algorithm over declarative knowledge have yielded comparable results? For Joscha, the question is, what's driving the shift from microsite to microsite 2? Is there something big that we should be hearing about that you didn't have time to tell us about? And for Pei, the question was, we got a lot of motivation in your talk. What's the new idea for how to deal with multiple goals and generation of goals and all of that? Is there kind of a one-liner we can take away from your talk?
Good questions. Who wants to start? Here? Yes. Maybe in the order there.
Yes, thank you. That's a good question. There's two parts to my answer. I think in some respects, if you take one domain, then it would be possible to perhaps replace the algorithm with another one, which would have similar effects. There's some properties of this kind of network which are important, the incremental learning, the way that the links are formed, and something I couldn't get onto was the way that larger levels of knowledge structure get built up, which are called templates. But yes, there's certain properties there that you could take and match with another algorithm. However, as a psychological model, CREST and EPAM before it have matched a whole range of experimental data going backwards in time. And in the early days, the micro details of the discrimination network, the way the familiarization and discrimination worked, were tested out with the verbal learning experiments. And as far as I'm aware, this is one architecture that matches that very, very closely, and the properties that came up with the humans doing the experiments. So I think that there's properties of the network which are critical across the whole range of experimental results, and in aggregate, that means that the sort of learning mechanisms in CREST make it fairly unique to match all of the data. Even if in one particular domain you might better replace it with something else.
With micropsi, there was the problem that some people actually started using it. It got us into trouble because it meant that we had to not only have Java docs and developer documentation for our guys, but we had to give support. And at some point we realized that it's very difficult to do support without a commercial model. And somebody offered us to do a commercial model and to pay us for giving workshops and so on, but this was with military money and very close military applications. So modeling of crowd control in Israel and so on. And me and a lot of the people which were working in the project at the time felt uncomfortable to getting too close to these sources for funding, and the purely academic sources were not open at that time for us. At least we didn't get project funding for it. And so this was one thing that we realized. We cannot give practical support beyond 1 or 2 teams. Because using it means extending it in interesting ways. For instance, one group wants to use robots with it, so we need to teach them how to build interfaces for robots. And then we realize, okay, we get into timing problems in this component, and we put this into the architecture. So in some sense, our model takes many lessons from the old architecture. Another one is that we build the software in such a way that it's much more maintainable than before. We find that it's much easier to understand the same code in Python than it is in Java. Literally last week we wrote a class from Java which comprised I think about 20 files in like 20 lines, and this is a big difference, and also it puts the fun back into what we do.
Yeah, if I have to pick one point in my talk, I think that will be what is called the functional autonomy of derived goals. Goal derivation happens in every AI system. You have goal, you have sub-goal, then you solve the sub-goal, eventually you solve the goal, which is taken by many people as, it should always be the case. But from my research, I think there is a very important factor here is if we study human cognition, you will see a lot of so-called human creativity, originality, a lot of things actually from goal derivation. So something initially was created as a means to achieve another goal, but it gradually grows into the goal itself. It becomes even more important than its parent goal that derives it. For example, why we want to do science, why we want to do AGI. How is that related to our daily life or our survival or reproduction rate or anything like that? We do it, for many people, just do it for fun. It becomes a goal by itself. Eventually in history, it actually starts from somewhere else. So I see a lot of value. And also I see it can be used, this notion can be used to represent or to interpret a lot of things in human cognition, which we also want in artificial intelligence. Also, I see that if we begin to make that assumption, you see a sub-goal, maybe not merely a sub-goal of its parent, then it changes a lot of things in your system design, in your resource management, in your evaluation, and so on. It will also relate to, for example, the social impact of AGI. That's why I picked this topic for this conference. I don't want people to assume, even if we are properly set an initial goal into AGI, become human friendly, it just, to me, that's not going to happen. So if I have to make one point, that's the point.
In the interest of time, we're going to take one last question and then we'll go to break. So.
Hi, I'm Fintan Costello from UCD in Dublin. I wanted to ask about all the models, how you deal with time. Time as a feature of it, of events, and events that span over time. is that easy to handle, or how do you handle it all? How do you deal with it?
Since I have the microphone, I think I will answer for you. Yeah, in my system, it is a long story. I can just say that in my system, time is actually handled in 3 different places. One is explicitly in the representation language. You can say that something happened, then something else happened. So that's kind of declarative representation. And also there is a procedural representation that the system will execute something, then execute something else within the system. Like in logic programming, there is sequence in operations. And also there is a system internal clock which we will use kind of like to manage its own operations. Say, I will do this, and I will wait for a minute, what I mean, then I will do something else. So all of the things, what is of course far from human level or perfect, but yeah, it's addressed in the design.
Okay, within CREST, obviously the model exists sort of within time, so as actions happen sequentially, there's a state of its memory based on the amount of experience at any particular time, but there isn't at the moment any specific thing internally for it to say, I learned this chunk on Monday and I've learned this one on Wednesday or anything like that.
In microsci, we deal with time very poorly. And I'd like to briefly highlight just a few bits on what we don't do with time but should do. So to start with, I think that time represents a partial ordering of events, and we have that. In special cases, it's distance, a temporal distance between events, and we have that, but we don't have all the measuring mechanisms that would be conceivable and necessary for doing that. Then time is the relationship to circadian clocks, which are built into the system, and there's more than one, and we don't have these. And time is the relation of internal events to outside events, and correlation between outside events. We have these partially. And the time is perceptual ticks. We don't have these. At all these, we ignore these, we could use them. Time, I think, is many more things than these. And one of what is most important is, at the moment, our agents store the world as a protocol of events, but I think it's much more a carpet of many, many world lines which are intertwined and are in complicated relationships to each other. And we have a very poor understanding of how this works. So I think looking at time for us would be a very productive thing to do, and it would be something which I would love to spend 20 years on.
Well, all these temporal features are more or less common to Octar, and we also had an additional problem that was, to synchronize with the video, with the visual input while it was streaming, and that required for us to optimize a lot of the system in terms of the query answer system to the external knowledge base, which is actually very fast right now, but it's also bound to the fact that we cannot make very complex inferences right now because of the time constraints. But of course it's a big problem, especially if you have to deal with artificial visual intelligence systems.
I can add to that, although I wasn't directly presenting the architecture, that in that architecture time is it's very much geared towards real-time processing. Goals, facts, and predictions all have time or time intervals, which if timing information is missing, it's completely incomplete knowledge. So that's an architecture with, I think, a relatively decent handling.
Speaking of time constraints, so we have about a 20-minute break, and then on this very long first day, we'll reconvene for the final session of the day.